Hi everyone. Today we're going to look at higher order derivatives and a very special higher order derivative called acceleration. Let's take a look at the do now together. Since the derivative of a function is itself a function, we may consider its derivative. If this is done, the result is again a function that may be differentiated. These are called higher order derivatives. So in other words, we could keep differentiating a function continuously. So we have the first derivative. This is the first derivative. This is the second derivative. We have the third derivative. And notice that the fourth derivative, we write a number, we put that number in parentheses, not to get confused by raising the function to the fourth power. So after the third derivative, we write the number and put in parentheses. Some books use Roman numerals, but I will use numbers. The fifth derivative, and the sixth derivative. So remember, we cannot go to the third derivative unless we have the second derivative. In other words, we keep differentiating it. We cannot get to the sixth derivative automatically until we have the fifth derivative, etc. So take a minute and find these derivatives given that polynomial function y equals f of x. Pause the video and write the derivatives. All right, so the first derivative, using the power rule and techniques of differentiation, we get 12x to the third minus 6x squared plus 2x minus 4. And keep in mind that the derivative of 2 is 0. It's a constant. Then when we differentiate the first derivative, we get the second derivative, and that would be 36x squared minus 12x plus 2. And again, the derivative of negative 4 would be 0. And we keep going. The third derivative would be 72x minus 12. And then the fourth derivative would be just 72. The fifth derivative would be 0. The sixth derivative would be 0. And any other derivative with order higher than 4 would be 0. So the order of the derivative is which derivative we're looking at. This is the order of the derivative. So we could say that for a polynomial of degree 4, when the fifth degree polynomial and on would be the fifth derivative and on would be 0. So we can generalize that for an nth degree polynomial, the n plus first derivative of the function would equal 0, and any order greater than that would be 0. So in this case, here, when n is 4, the fifth derivative would begin equaling 0 and on. All right, so let's see what this represents geometrically. So the first derivative of f represents, now we could say, the instantaneous rate of change of f. We could also say the slope of the tangent line on the graph of f. All of these are synonymous. Similarly, the first derivative represents, the second derivative represents the same thing. The instantaneous rate of change of the first derivative of f, or the slope of the tangent line on the graph of the first derivative. And similarly, the third derivative of f represents the instantaneous rate of change on the second derivative of f's graph, or the slope of the tangent line on the graph of the second derivative. So we're extending our idea of instantaneous rate of change or the slope of the tangent line to subsequent graphs. All right, now let's look at notation. So if we call our function y equals f of x, one popular way to represent successive derivatives or higher order derivatives is with the little tick marks, or after the third derivative, we put the number, the order, with parentheses. But another way to write this is in slope form. We read this as the derivative of y with respect to x. And on your calculators, you do have a dy dx key when you graph the function and you go to menu and you look at the options. They do have a dy dx key to get the slope of the tangent line to a given curve at any point. Now, the second derivative is the derivative of the first derivative. So I will write this. The derivative of the first derivative. And this can be abbreviated as follows. It's not an exponent. Notice that this 2 is in different places. It's almost like we're squaring the dy, but not. We're just finding two successive derivatives. So this is read the second derivative of f, or the second derivative of y with respect to x. The third derivative is the derivative of the second derivative. And we can abbreviate this as follows. D superscript y over dx superscript 3. And this is exactly where we place the superscripts, right? They must be placed there. And then the fourth derivative is the derivative of the third derivative. And you guessed it, we could denote this as d superscript 4 y over dx superscript 4. So the nth derivative of y can be represented as d superscript n y over dx superscript n. So this is a fancy way of representing the nth derivative in that slope form. But again, I emphasize it's not an exponent. So that's why we place those numbers in different places. Okay, now if we're going to use the function f, then the first derivative can be written as the derivative of x, the derivative of f with respect to x, and the rule of the function could be put here, or we could just write f of x. All right. The second derivative is the derivative of the first derivative, which can be written like this. Just like the other one, but the superscript is right after the first d, and we write the function here. And the third derivative, which is the derivative of the second derivative, is d superscript 3 of f of x over dx superscript 3. So the fourth derivative would be d superscript 4 of f of x over dx superscript 4. And the nth derivative of f can be written as d superscript n of f of x over dx superscript n. Keep in mind, if you compare these notations, in this one, we're replacing the y with f of x, but it's basically the same notation. So we could either put y for f of x, or we could put down the rule f of x in brackets. Okay, let's move on. Now let's discuss how to find a higher order derivative at a particular given x value. I wrote as the given point x1. So, for instance, if in 3a, given y equals f of x, find the derivative of f at x equals 3. Okay, now in class, we've been denoting it this way: the derivative of y at 3 and the derivative of f at 3. But another way to write it is to write the derivative of y with respect to x using that slope notation, a vertical bar at x equals 3. This means the same as what I've circled in yellow. It's the derivative of y with respect to x at x equals 3. So first we differentiate and then we substitute 3 for every x. Another way is to write it in this d, the derivative of f of x with respect to x, vertical bar at x equals 3. And your calculator uses these two notations, particularly this one. When we go to the key next to the book, you will have an option, D box, right? A D with a box here, and a D box, vertical bar, and then we type in x equals 3. All of these do the same thing. The last one that I circled in blue is more compact. We don't need to know what f of x is because f of x is written out for us, the rule. Now, the second derivative of f at x equals 3 can be denoted this way, which is what we've been using in class. But using the dy dx notation, we could write d superscript y over dx superscript 2, d superscript 2y over dx superscript 2, and then a vertical bar. I couldn't make the vertical bar on my computer, at x equals 3. So this means the second derivative of y with respect to x at x equals 3. So we first find the second derivative, and then we substitute 3. In a similar way, we could write it this way: d superscript 2 of f of x over dx superscript 2, and with a vertical bar at x equals 3. So let's take a minute and write the third derivative of f at x equals 3, the fourth derivative of f at x equals 3, and the nth derivative of f at x equals 3 using parts A and B as a guide. So pause the video and try it. All right, I've written in the answers for you, and they're really very similar to part C. If we follow the pattern, notice with the fourth derivative, we put the parentheses around the 4, not to get confused with raising the function to the fourth power. And again, as we said, this is the most compact notation, or this. So let's practice the last notation with 4 and 5. So if we do 4 together, first we have to keep track of our derivatives, the order of the derivatives. So our function here, okay, I need a vertical bar here because I couldn't type that in. So our function here is y equals x to the 5th. And we want to get the third derivative. So let's label it. We have 5x to the 4th for the first derivative. The second derivative is 20x cubed. The third derivative would be 60x squared. So notice how I kept track of our function with the derivatives. Please label each step clearly. So once we get the derivative rule, we substitute in our number, which in this case is -1. So we get 60 times -1 squared, and that gives us 60. So our final answer here is 60. Okay, so please don't forget to write this down. All right, so our function here in number 5 is y equals x to the 1/2. So try this one yourselves. Get the fourth derivative and label each step. Label the first derivative, the second derivative, the third derivative, and the fourth. You have to go through all those derivatives to get to the fourth derivative, and then substitute 9. So take a minute and try it. Pause the video. All right, so let's take a look at this work. So we use the power rule with fractional exponents. We rewrite y equals x to the 1/2. And when we differentiate using the power rule, the first derivative is 1/2 x to the negative 1/2. We bring this 1/2 to the front, and we get negative 1/4 x to the negative 3/2 for the second derivative. Then we have the third derivative, so negative 1/4 times negative 3/2 gives us positive 3/8 x to negative 5/2. Remember, we always subtract 1. And then finally, the fourth derivative is negative 15/16, which is negative 3/8 times negative 5/2, x to the negative 7/2. Now moving up here, we substitute 9. So we rewrite x to the negative 7/2 as the square root of 9 to the 7th. Now keep in mind here that in class, we had said that this is equal to 1 over the square root of x to the 7th. But we could also write it as 1 over the square root of x, that to the 7th power, which is really easier than raising x to the 7th power and square rooting it. So using a calculator, I multiplied 16 times 3 to the 7th, and my answer was negative 15 over 34,992, which is right here. Right here. Okay. So, again, I'd like to emphasize that this is a fine answer. I'd like to highlight that in red. This answer is also fine. Negative 15 over 16 times 3 to the 7th. All right. Now let's take a look at how acceleration comes into the picture. So here I'd like to review the position function. I picked a very simple one to demonstrate acceleration numerically. So let's get the derivative of the position function, which is the velocity. So we know that the velocity function is the first derivative of the position function, and in this case it would be 8 minus 2t. So let's complete the table for a position and velocity. Speed is the absolute value of velocity. So speed is always greater than 0. Velocity could have a sign which tells us the direction when the particle is moving right or left. So let's fill in the table. So we want the time we want the position at time 0, and we want the velocity at time 0 and the speed. For instance, I'll do 5 for you. So when t equals 5, the position is 15. The velocity, I'm sorry, I put it in the wrong spot. The position is 15. The velocity is negative 2. And the speed is 2, because it's the absolute value of the velocity. Okay, take a minute and fill in the rest of the chart. So the chart has been completed here. And again, I substituted the time values into the position function and this velocity function, which is linear. All right, so now the question is, how is the velocity changing? Notice that the velocity is decreasing by 2. And every subsequent velocity is found by subtracting 2. And we can find this -2. How can we do that using the velocity equation? Well, if we differentiate the velocity equation, the derivative of 8 is 0, and the derivative of -2t is -2. So the derivative of the velocity is called acceleration, which tells us the rate of change of the velocity. So the velocity is decreasing. Let's write that down. The velocity is decreasing at a rate of, so let's revise this. Decreasing at a rate of, so whatever the units are, let's say 2 centimeters per minute would be the unit for the velocity, but because we're describing the rate of change, we have to put it over minutes. So we could say 2 centimeters per minute, which we could abbreviate it as per minute squared. Oh, okay, so let's define acceleration. Acceleration is the rate of change in the velocity with respect to time. And again, if this is our position function, the first derivative of the position function gives us velocity, and the derivative of the velocity gives us acceleration. But that is the second derivative of the position function. So we'll write x double prime t. So the second derivative, the acceleration, is always in terms of the y unit, let's say centimeters, per time squared, which is minute to the second, or the unit for the velocity per time. Okay, so let's take a look at speed. How does speed come into the picture? Well, here the acceleration is always -2. So the acceleration here is always negative. And notice that the speed here is decreasing. Oh, decreasing. Let's just erase this now. Okay. Here, when the velocity is 0, the speed is 0. And from here on, the speed is increasing. And if we take a look at the signs of the acceleration and the velocity, well, the acceleration is always negative because it's -2, right? And the velocity, well, here when the speed was decreasing, the velocity was positive, right? If we look at these numbers. And here, when the speed is increasing, our velocity was negative. So can we make a conjecture of when a particle is increasing or decreasing speed, looking at both the signs of the acceleration and the velocity? Well, let's fill in our part D. So we know that the particle increases speed in the time interval from 0 to 3. And it decreases speed in the interval from 5 to 7. Well, to think about it, it says it decreases speed. We could say from 0 all the way to 4. Let's put 4 in here because a particle stops there at 4. And that it increases speed from 4 to 7. So we have 4 in the picture. All right, so let's make a conjecture. What is true about the signs of the velocity and acceleration when the particle decreases speed? Well, looking at our chart, the signs are opposite. The signs for A of t and V of t are opposite, meaning that one is positive and the other is negative, or vice versa. But when the signs of the velocity and acceleration are the same, in this case they were both negative, then the particle increases speed. Meaning that they're either both negative or, in the same way, both positive. But I wanted to illustrate the two negatives that we increase speed. So let's summarize. When v of t, and this is very important, when the velocity and the acceleration have the same sign at a certain time, then the particle increases speed. When the velocity and acceleration have opposite signs at a given time, then the particle decreases speed, which is synonymous to slows down. All right, so this question has often been asked on the AP frequent response question in the long answer. And nowadays, they would ask something like the next question. Now, this is the position function that we analyzed in our lesson on the power rule and techniques of differentiation. And we found that finding the velocity, well, let's do that. So with the velocity function is t squared minus 6t plus 8. And we found when the particle stops and when the particle moves left or right. Remember that the particle moves right, left, and then right. Now the acceleration function here is just 2t minus 6 when we differentiate the velocity. So if we wanted to show that the particle slows down at t equals 1, all we have to do is substitute 1 into the velocity and the acceleration and see what we get. So we get 1 squared minus 6 times 1 plus 8, which gives us 1 minus 6 plus 8. And that gives us 3, I believe, which is greater than 0. And when we put 1 into the acceleration, we get negative 4, which is less than 0. So we say the particle slows down at t equals 1 because A of 1 and V of 1 have opposite signs. Okay, similarly, we could show part B by substituting 2.5 into our velocity and acceleration. And if we could possibly compute these right and figure out just the sign, we don't have to get down to the number. We just have to see if our answer is positive or negative. We get 2.5 squared minus 6 times 2.5 plus 8. And that answer is negative. It's a negative 0.75, which is less than 0. Now we have to look at the acceleration at 2.5, which is 2 times 2.5 minus 6. Well, that's 5 minus 6, which is negative 1, which is less than 0. So our answer is the particle is increasing speed at t equals 2.5, since the velocity at 2.5 and the acceleration at 2.5 are both negative. Or you could say both have the same sign. But this has to be written on the AP. So remember, to predict speed of the particle, we must look at both the acceleration and the velocity. And the acceleration function is found by taking the second derivative of the position function or the first derivative of the velocity. Let's take a look at an animation for this particular question on Desmos. Hi, so I wanted to show you an animation on comparing the velocity and acceleration of a particle. This position function we already discussed in class when we were using the power rule and the techniques for differentiation, except I put a t instead of an x. And we started with time greater than 0, and we're going to plot the position, the velocity, and the acceleration and compare them and see when the particle's speeding up and slowing down. Now, remember that when we analyzed the velocity, we found that the particle moves right, left, and right. Okay, so that's the position. It should go right, left, and right. But I'd like you to compare the velocity and the acceleration at the corresponding times. And you'll see that when the velocity and acceleration are moving to the right, both to the right or to the left, the particles picks up speed. And when the velocity and acceleration are in opposite directions, the particle is actually slowing down. So let's watch the animation. Okay, so now the particle's moving to the right, it's slowing down. The acceleration and velocity are in opposite directions. And now the particle is going to move to the right. It might speed up a little bit because the velocity and acceleration are in the right. But then, and we see that it picks up speed because they're all going toward the right. Now, when the particle comes back, notice that the velocity and acceleration are both negative, and the particle is picking up speed. So that's one animation that we have already discussed. So you can replay that if you'd like, and to convince yourselves. There's another animation I'd like to share with you in GeoGebra that is a little bit more detailed, and that is this one here. Okay, I'm going to go now to the next one. It's motion of a particle in one dimension. It's this girl walking her dog. Let's just get this on full screen if I can do that. Okay, so here, this girl is walking her dog. This is the position function. Here's the acceleration and here's the velocity. But it's really nice because in this animation, they give us the position at the time, the velocity at that time, and the acceleration at that time. And it also tells us which way the girl's moving, right or left, when she's speeding up or slowing down. So let's check this one out. So I'm going to start the animation, but it goes rather quickly. At 3.9, we see that the velocity and acceleration are both positive. So the girl is moving to the right and she's speeding up. All right, so let's look at the animation. So it's rather quick. All right, she's really speeding up when the velocity and acceleration are both positive, but let's try to stop the animation when the velocity and acceleration are both negative. So right here, if I could, oh no, let me try again. Okay, here. So notice that at 0.4, she's moving to the left, and the acceleration is negative, and she's speeding up. So I thought that was a very cute animation as well. I like the numbers here because they really compare the numbers, the direction, and the speed at the same time. And when she is moving to the left and the right. Okay, so that takes care of the animation. And just remember, when the velocity and acceleration at a certain time are the same sign, then the particle speeding up. When the acceleration and velocity are opposite signs at a certain time, then the particle is slowing down. And that's what we use in calculus today.